Okay, let's do question 3. We're meant to be proving that if you start with a non-empty list of non-empty lists and you concatenate them all together, what you get is a non-empty list. Let's work backwards in this example and actually start with the theorem. So let's give it a good name. Let's call the operation of taking a whole list of lists and sticking them all together, let's call that glom. So in that case, the canonical mathlib name might be something like non-empty glom of non-empty, something like that. Okay, and what does it actually say? It says that if you have L, a list of lists of alphas, and you have the fact that L is non-empty, and you have that for all lists that appear in L, that list is non-empty. Oh, sorry, I better give that a name. W. Then we have that when you glom everything together, what you get is non-empty. Okay, at this point, and let's of course write sorry. So Lean is of course complaining, it doesn't know what's going on here. It doesn't know what alpha is. You can fix that by typing variable alpha as a type. And then it's saying that it doesn't know what glom is. And it's a little bit confused actually about what non-empty is. So it seems like non-empty is something that's already built into Lean. It's for talking about a sort or a type being non-empty. So maybe let's just put a prime on it so we can have our own non-empty in a moment. Okay, so we need to define glom and non-empty. Let's do those. So glom is going to be something that takes a list of alphas and produces a list of alphas. And our non-empty is going to be something that takes a list of somethings and produces a proposition. Okay, so at this point we have no red lines, nothing is undefined, just lots of green lines because we haven't actually defined things. Let's actually begin the proof, even though not everything is, even though nothing is really defined, just to see how it's going to start looking. So what's the proof strategy going to be? Well, almost certainly we're going to define non-empty and glom by list induction. So probably that means that the proof is going to also proceed by list induction. So let's type induction L. Okay, that gives us two goals, one in the case where L is nil, another case where list is cons. And so at this point we probably really better start filling in definitions, or we're not going to be able to do anything. So let's go and do glom. In fact, I don't want to write glom quite like this because I want to use the pattern matcher. And to use the pattern matcher I need to move the arguments to the right of the colon. So let's just rewrite the type signature like that, and remove the colon equals, and now use the pattern matcher to say that glom of the empty list of lists is the empty list, and otherwise glom is, well, you take the head list and you concatenate it with the result of glomming the tail list. If I really wanted to do things from scratch, I could define list concatenation myself here, but I'm just going to use the built-in mathlib one. Similarly, let's define non-empty. We're also going to define this using the pattern matcher, so let me just rewrite the signature. Like so. The point of the definition here is that non-empty of the empty list is false, and non-empty of anything else is true. Okay, so how might we proceed? Well, we need to use the fact that glom of list nil is list nil, and hopefully I can do this by simp. Well, that doesn't work. I could at this point go away and you say desimp glom, and that will work. That'll unfold the definition. But really better is at this point if I write a lemma that explicitly restates the fact that glom of nil is nil. And this should be easy to prove. I can just prove it by ruffle. And of course, the point of doing this otherwise boring restatement is that we're marking it as a simple lemma, so the simplifier will use it in future. There's an error here. It says it doesn't know what type we're talking about here. Notice that alpha doesn't appear explicitly anywhere in this lemma, and I think that's what Lean's getting confused about. So let's just add an explicit type annotation here so that Lean can see what we're talking about. Okay, so now we can go back to this first case and just try running simp. And that works great. We see that the goal is to prove that list nil is non-empty. Now, that is a terrible goal because of course it's false. So at this point we should realize that simplifying wasn't actually what we wanted to do at all. We should look at the hypotheses, realize that one of the hypotheses is absurd, and run cases on that, and hope that Lean can see that there was no possible way to have built that thing. And indeed that's right, that dispelled the first goal. So let's wrap that up in braces for clarity. Okay, on to the second case. We probably at this point should unfold the definition of glom of this cons, but again, let's write a simple lemma so that the simplifier can do that for us. This time there are actually a few arguments. Oops, I didn't call them head and tail here, I called them little l, big L, and then this is just little l plus plus glom big L. And again, that's proved happily by ruffle. Okay, so in this branch, let's run the simplifier, and the goal is now to prove that if you take L head plus plus glom L tail, that whole thing is non-empty. How are we going to do that? Well, first of all, let's give things better names. I don't like having to talk about L head and L tail. So let's go change this first line to induction with little l, big L. And so, of course, the point is that we know that little l is non-empty. And one can show, of course, that if the left-hand thing in a concatenation is non-empty, the whole thing is non-empty. So we should be able to proceed like that. So let's at least state that lemma. So what is it going to be? It's going to say that I think that's probably the pretty close approximation of the canonical mathlib name. So this says we have two lists, and we have a witness that the left one is non-empty. Then we can conclude that the concatenation is non-empty. Now, let's definitely not prove that at this point. It would be a disaster. It would be stupid to prove this lemma at this point, because in the theorem we really care about, we're not actually sure that it's going to be useful. Our idea for proceeding is to use this lemma, but we haven't actually worked all the way through the proof, so we can't commit. So I think it's really useful to remember that you can leave this lemma as sorry for now, and see if you can make the rest of the proof work. So at this point, we're actually just ready to use this lemma, so let's just apply it and see that that means the new goal is non-empty L. How are we going to prove that? Well, actually, we've got a hypothesis that tells us exactly this. It says that if you've got any list, and that list is a member of little l cons big L, then that list is non-empty. That was, of course, our hypothesis in the theorem to begin with. So we just want to use that fact. In fact, we just want to apply that fact. We can literally do that, right? Apply W, and that unifies some of the parameters, and Lean has worked out that the remaining thing we need to prove is that L is a member of the list little l cons big L. Now that's just a very basic fact about lists, so hopefully we can prove it with simp. Indeed we can. That's great. Our strategy for the big theorem worked, so as long as we can go and fill in this lemma, we're all set, so let's try and prove it. How do we prove it? Almost certainly we prove it by induction on P, since everything's defined in terms of P. In the first case, we've got the hypothesis non-empty list nil, which, as we saw before, is absurd. And otherwise, we've got the fact that something cons something 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 is non-empty. And of course, that's just by the definition of non-empty true. And so since we're trying to prove a goal here that is definitionally true, we're allowed to just use trivia. Okay, that finishes off that goal. We've now got no green or red squirrels anywhere, so our theorem is proved. Maybe before we finish, let's just recognize one final thing. In this induction here, we didn't actually use the induction hypothesis. In this second branch, you'll see there's this extra hypothesis, LIH, which tells you that this theorem was true for the shorter version of L that we came up with through the induction. We didn't use it because, of course, the proof worked just by looking at the little l there and using the fact that it itself was non-empty. So since we're not actually using the inductive hypothesis, we could arguably slightly clean up this proof by just doing cases instead of induction. And then in this branch of the theorem, the inductive hypothesis doesn't appear, and we can't be confused by the fact that we are not using it. Okay, looks good.